Hello there. My name is Albert Farah, and I'm currently a freshman at the University of Massachusetts Lowell. This past year, as a senior at Medford High School, I conducted research on enhancing positron propulsion techniques with multiple beam generation. In 2018, a NASA-funded team proposed and began investigating a next-gen propulsion system that uses beams of antimatter, positrons or anti-electrons, to ignite a dense fusion fuel and provide interplanetary and interstellar spacecraft with a high-thrust, highly efficient propulsion system. Reactions between antimatter and matter, known as annihilations, are the most energetic reactions known, releasing orders of magnitude more energy than even the most energy-dense nuclear reactions. By combining the two most energy-dense reactions, fusion and annihilation, into a propulsion system, the team's proposed system promises numerous opportunities for fast transit deep space exploration. In their design, the energy of the fusion reaction increases with the number of positrons deposited onto the fusion fuel. As a result, more positron beams would increase the thrust delivered by the system. Storing, trapping, and accumulating antimatter into beams is difficult, though. The high-energy particles first have to be slowed down or moderated before being stored. Antimatter also wants to annihilate and turn into gamma radiation with its matter counterpart wherever possible, so matter cannot interact with the antimatter directly while storing it. Extremely strong magnetic and electric fields must be used to form traps that contain the antimatter, and since a limited number of positrons can be stored in those traps, the beams that use those positrons can only have so many of them per beam pulse. I propose a design for a positron capacitor that uses the energy of the positrons in the beams to subvert the upper limits on the positron populations of those beams. This opens up this propulsion system to applications requiring even higher thrust for briefer periods of time, such as spacecraft maneuverability. Instead of bunching many positrons into a single beam, I investigated a method of using the energy of the positrons to generate more independent positron sources, from which many beams could be produced, effectively increasing the amount of antimatter that could be deposited onto the fusion fuel and used for thrust, without attempting to push that upper limit of the population in the beams. I simulated elastically scattering two initial positron beams so that the positrons would be scattered all over a volume space. When the positrons in one beam collide with those in the other beam, they scatter in different directions, retaining the total momentum and energy between them. Using the J-OUT4 simulation toolkit, I simulated using a uniform magnetic field to cluster these scattered positrons, creating two groups of positrons that contained the same number of positrons as the beams they came from, but were located in a different part of the volume space that then was targeted by either of the original beams. I devised a model to relate the energy of the scattered positrons to the strength of the magnetic field that produces the densest cluster, hypothesizing that a greater magnetic field would result in a denser cluster. The densest cluster was found by maximizing the ratio of the cluster population to the cluster spread. There turned out to be a sweet spot for the best magnetic field. Too weak, and the positrons would not be grouped very well. Too strong, and they would distribute themselves along the axis of the uniform magnetic field. As you can see, there's a very distinct linear relationship between the beam energy and the square of the magnetic field that creates the densest cluster. This relationship is also derivable from theory, using the expressions of the non-relativistic momenta and energy of the positrons, as well as the Lorentz forces that the positrons experience in the uniform magnetic field. The noise in the measurements increases with the positron energy, appearing to be an artifact of the simulation trying to track faster particles. The positrons of the densest cluster possessed randomized momenta, parallel or antiparallel to the direction of the uniform field, making the cluster very closely resemble conventional positron sources for beams, such as radioisotopes. The positrons in the proposed design actually are decay products of the radioisotope Krypton-79. This reassured me that these were effectively virtual positron sources that could supply the independent beams. I found that changing the orientation of the magnetic field maximizes the number of positrons that can be formed, because one group of scattered positrons are being localized into a different region of space than the other groups of the scattered positrons. Over time, each cluster location acts like a new source for beams. From each of these clusters, a separate beam can be made, and a single unit producing many clusters can store many more positrons than a single beam ever could. I also wondered if I could use the positron's energy to directly contribute to the clustering process. So I explored using the clustered positrons to provide the current required to generate the optimal magnetic field, supposing that Helmholtz coils, which are solenoids, would provide the uniform field. I used experimental and simulated data from other studies on positron-induced secondary electron current generation, a process in which positrons knock off secondary electrons as they pass through the material, producing a current. Traditionally, electrons are used to knock off the secondary electrons and induce the secondary electron current, but several studies have shown that positrons induce the same process nearly to the same degree in a variety of materials. As a result, I was comfortable using the expression for the electron-induced secondary electron yield law for my project, where positrons would be inducing that yield instead. For specific elements, I combined this secondary electron emission law with transmission parameters from another study's Géant simulations, with my model of the optimal magnetic field, and the relationship between the current running through the Helmholtz coils and the magnitude of the magnetic field that they generate, to find the minimum beam populations and energies required to generate the secondary electron current in certain elements. I set a minimum number of positrons that have to escape the transmission material so that they can be used for thrust. And I set that to a certain fraction of the clustered positrons that actually entered the material. Those positrons that did not escape would induce the secondary electron current. Using my model relating the positron energies to the optimal magnetic field, and given that a current running through the Helmholtz coils would generate the field, I calculated the number of positrons that would be required to generate the current. As seen, all of these elements require fewer than 500 positrons to generate the current for the optimal magnetic field. Since particle beam bunches contain orders of magnitude more positrons, the actual generated current would be significantly more than what would be required to power the Helmholtz coils. Additionally, as is intuitive, I found that decreasing the minimum required positron population that escapes the material decreases the energies those positrons need to generate the secondary electron current, since more positrons are being used to create the current, so they don't need as high of an energy to generate that current. In essence, this proposed system takes two positron sources and uses the energy of the positrons to spread them around a defined volume. The positrons that are clustered by the uniform magnetic field can then be collected and bunched into their own beams as though they were independent positron sources. New groups of positrons from the initial sources will be clustered by a differently oriented magnetic field and collected in a different section of the defined volume, where they can be stored and bunched into their own beams. As a result, the number of beams that can be produced from the initial two is only limited by the defined volume. And with multiple of these units, the number of beams that can be created increases exponentially. The next major step in my work is establishing parameters for the two initial beams that will maximize the variety of the scattering trajectory of the positrons so that we can make more sources. My research is an alternate approach to antimatter storage, introducing a novel system for a positron capacitor that can dramatically increase the capability of a positron-powered propulsion system. In addition to advancing in-space propulsion engineering, a positron capacitor opens up untold avenues for advanced electronics research. Imagine the logic that could be built around antimatter circuitry. These systems could exploit the various properties of antimatter and its energy-dense reaction with matter, opening new research into applying antimatter technology. Finally, I'd like to thank Dr. Michael Wadness, my AP Physics teacher while in high school, for offering guidance, encouragement, and much-needed critique of this ongoing research through its developmental phases. They were extremely invaluable and important to the progress of this work. Thank you for your time, and I'd love to answer any of your questions.